Welcome back. Here's a saying I want you to carry into every AI audit you ever do. The model is the mirror, but the data is the face. Whatever the data looks like, the model will faithfully reflect it flaws, gaps, prejudices, and all. So, this chapter takes us deep into the data behind the model, and honestly, this is where most real audit findings are born. So, what are we focusing on? First, following the data. We'll trace it through training, validation, testing, and production, and learn to verify source credibility, legal rights, and lawful basis at every step, because data with a shady origin poisons everything built on it. Second, quality and integrity. The dimensions that matter completeness, accuracy, representativeness, and how to detect tampering through access controls and audit trails. Third, the hunt for bias, where it hides in training data, how lineage records, model cards, and dataset cards serve as your audit evidence, and why proxy variables and stale features quietly smuggle discrimination back in. And fourth, the synthetic frontier, artificially generated data, its fidelity and privacy trade-offs, and the uncomfortable ways it can amplify bias and mislead auditors, ending with a practical checklist you can carry straight into fieldwork. If you audit the data well, the model has nowhere to hide. Subscribe if you haven't yet, and let's follow the data. Let's begin with a discipline I call walking the data. Before you judge any model, you should be able to trace its data through four distinct territories: training, validation, testing, and production. Sounds procedural? Stay with me, because each border crossing is a place where things go quietly wrong. Quick refresher from Chapter 3. Training data teaches the model. Validation data tunes it. Test data gives the final honest exam. And production data is the real world flowing in after launch. Four datasets, four different jobs. Now here's the auditor's twist. At each stage, ask two questions. Is this the right data for this job? And has it been kept separate from the others? Why the obsession with separation? Remember our coaching center analogy. A student who peeks at the board exam paper, scores brilliantly, and knows nothing. Same customer in training and test sets. Same effect. But there's a subtler crossing people miss, the border between test and production. I once reviewed a fraud model whose test performance was stellar. Then we compared the test data against live production traffic, and they barely resembled each other. The test set was 3 years old from before the company launched digital payments. The model had passed an exam for a world that no longer existed. So how do you actually walk the data? Request the data flow documentation and follow one dataset end to end. Where was training data extracted? When? By whom? How was the split performed? And where's the evidence the test set stayed sealed? And critically, how does production data get compared back against training data? That's your drift bridge from Chapter 3. Here's your habit. Never accept performance numbers until you know which territory they came from and how old the map is. Numbers without geography are just decoration. Now let's interrogate where the data came from in the first place, because a model built on questionable sources is a house built on someone else's land. 3 checks today: credibility, legal rights, and lawful basis. And yes, they are 3 different things. Let's untangle them. Credibility first. Is the source trustworthy, current, and fit for purpose? Data purchased from brokers, scraped from websites, or aggregated from partners arrives with a confidence problem. Who collected it originally? How and when? I once examined a marketing model trained partly on a purchased demographic dataset. When we sampled it against known customers, nearly a fifth of the attributes was simply wrong: stale addresses, misclassified income bands. The vendor's glossy brochure said premium data. The evidence said expensive guesswork. Ask for source documentation, sample-based verification, and freshness dates. Credibility is testable, so test it. Legal rights next. And this is about ownership and permission, separate from privacy. Do we have the contractual or license right to use this data for training? Web scraped content may violate site terms. Partner data may be licensed for analytics but not for model building. Remember my story from the lineage lesson, the scraped partner portal? That was a rights failure and it made a flagship model legally radioactive. The evidence you want, licenses, contracts, and terms that explicitly cover machine learning use. The phrase "we've always had this data" is not a right, it's a habit. And third, lawful basis, the privacy dimension from Chapter 8. Even with credible licensed data, personal data needs a documented legal ground for this specific processing. Three different questions, three different documents. And here's the field reality. Organizations usually can answer one of the three. Your job is asking all three for every significant source. When one dataset passes all three checks with evidence, you've found maturity. When none do, you've found your executive summary. Time to get precise about what good data actually means. Because quality is not a feeling, it's a set of measurable dimensions. Today, the three that matter most for AI: completeness, accuracy, and representativeness. And I'll show you why the third one is the sneakiest. Completeness asks, is anything missing? Missing values, missing fields, missing populations. Now, some missingness is random and survivable. The dangerous kind is patterned. Imagine income data that's missing mostly for gig workers and informal earners because legacy forms never captured them well. Delete those incomplete records. Remember our pre-processing lesson, and you've quietly deleted a demographic. The model then learns a world where those people barely exist. So don't just ask what percentage is missing, ask who is missing. Accuracy asks, is the data correct? Does it reflect reality? Wrong ages, outdated addresses, mislabeled outcomes. And in supervised learning, label accuracy is everything. If human reviewers label transactions as fraud inconsistently, the model learns their inconsistency as truth. Here's a practical audit move. Sample a few hundred records and verify them against an independent source. Tedious? A little. Revealing? Almost always. Now representativeness, the sneaky one. The data can be complete and accurate and still describe the wrong population. Ask yourself, does this training data statistically resemble the people the model will actually judge? A credit model trained on urban salaried applicants deployed nationwide meets rural gig workers it has essentially never seen. Every prediction for them is an educated guess wearing a confident face. The famous facial recognition studies found exactly this: systems performing beautifully overall while failing dramatically on darker-skinned women because the training photos skewed heavily elsewhere. Overall accuracy hid segmental blindness. Your takeaway? Request quality metrics on all three dimensions, and for representativeness, demand the comparison: training population versus deployment population, side by side. If nobody has ever drawn that comparison, the model is navigating with someone else's map. So far, we've assumed data problems are accidental. Now let's assume something darker, that someone changed the data on purpose: tampering. Because here's the strategic insight. If you wanted to corrupt an AI system, you wouldn't attack the model, you'd attack its food supply. Today, the controls that protect it and how to audit them. Why is training data such an attractive target? Think about it. Change the model's code and code review catches you. But nudge a few thousand training labels, mark certain fraudulent patterns as legitimate, and the model learns to wave your fraud through, permanently, invisibly, with no alarm. We'll cover data poisoning as an attack in Chapter 15, but the defensive controls belong right here in the data chapter, because they are the same controls that protect against insider mischief, vendor errors, and plain unauthorized fiddling. Control Family 1. Access Controls. Who can read, write, and modify training datasets, feature stores, and labels? The principle is least privilege, and the field reality is usually the opposite. Data science teams sharing broad access to everything, service accounts with God rights, and extracts sitting in personal folders. Ask for the access list on one critical training dataset and watch how long it takes to produce. Then ask the harder question: who can modify labels and does anyone review those modifications? Control Family 2. Audit trails. Every change to significant data should leave a footprint: who, what, when. Immutable logging, version-controlled datasets. Remember data versioning from Chapter 6, and checksums or hashes that make silent alteration detectable. A dataset with a verifiable fingerprint can be proven unchanged between validation and training. No fingerprint, no proof. And the connecting tissue, anomaly monitoring on the data itself, sudden shifts in label distributions, unusual bulk updates, edits at odd hours. Here's your simple field test. Ask the team, if someone altered 1,000 labels last Tuesday, how would you know? A crisp answer means controls exist. A thoughtful pause means the food supply is unguarded, and you know how to write that up. Now for the lesson this chapter has been building toward: bias hunting. Everyone agrees bias data is bad, but where exactly does bias hide? Because it rarely announces itself. It hides in respectable looking columns. And today, I'll teach you the hiding places. Hiding place 1: historical decisions. Supervised models learn from past outcomes, and past outcomes carry past prejudice. The Amazon hiring tool remains the perfect teaching case. Trained on a decade of hiring decisions, it learned that patterns associated with women predicted rejection because historically they had. Nobody typed discrimination into the code, history supplied it. So ask, whose past judgments became today's labels? Hiding place 2: measurement gaps. Bias creeps in through what was never recorded. A lending model can't learn that rejected applicants would have repaid. It only sees outcomes for the approved. So the historical rejection pattern feeds itself. Remember our feedback loop from Chapter 3? Similarly, the healthcare algorithm case we'll study in Chapter 20 used healthcare spending as a proxy for medical need, and because less money had historically been spent on black patients, the model rated them healthier than they were. The bias hid inside the choice of what to measure. Hiding place 3: sampling skew, our representativeness lesson wearing its bias hat. Underrepresented groups get lower quality predictions, and low quality at the margins is how disadvantage compounds. Hiding place 4: labeler subjectivity. When humans label toxicity, creditworthiness, or suitability, their assumptions ride along. Ask who labeled the data, with what instructions, and whether interlabeler consistency was ever measured. So how do you hunt? Profile the training data across demographic groups, compare distributions, question the label's origin story, and trace what each proxy actually measures. And keep this reframe close. You're not asking, is the data biased? All human data is. You're asking, did anyone look? What did they find? And what did they do about it? Silence on all three is the finding. Let's talk about paperwork, but the good kind. The documentation artifacts that turn data governance from folklore into evidence. 3 stars today: lineage records, dataset cards, and model cards. Learn to read these and your fieldwork accelerates enormously. Lineage records first, familiar ground from Chapter 8, the documented journey of data from source systems through every transformation into the training set. Modern data platforms can generate lineage automatically, which means for many organizations, the honest answer to "show me the lineage" is a tooling question, not a heroic archaeology project. When it's missing, ask why, because the absence is itself informative. Now, dataset cards, sometimes called data sheets for datasets, an idea borrowed from electronics, where every component ships with a specification sheet. A dataset card documents what this data is, who collected it, why, how, what it contains, known gaps and biases, licensing and consent status, and recommended and discouraged uses. Read that list again as an auditor. It's practically a pre-answered evidence request. A team that maintains dataset cards has already asked themselves your questions. A team that hasn't will discover the answers live in front of you which is always educational. Model cards do the same job one level up, documenting a model's purpose, training data, performance across segments. Remember, harm hides in segments, limitations, and intended use boundaries. When a model card honestly states, this model was not evaluated for use on populations under 18, and you find it deployed in a student-facing product, the finding writes itself, and the card is your evidence. Here's the mature perspective. These cards aren't bureaucracy. They're institutional memory in a field with brutal staff turnover. Remember our handover lesson. And here's the audit subtlety. Check the dates and versions. A model card frozen at launch while the model has retrained 5 times is a museum plaque describing an exhibit that left the building. Living documents or lovely fossils, that's the distinction your report should draw. Now we enter genuinely modern territory, synthetic data, artificially generated data that statistically resembles the real thing. It's being sold as the answer to half of this course's problems: privacy, scarcity, imbalance. Some of that promise is real. Let's understand it properly before next lesson, where we'll see how it bites. What is it? Instead of using real customer records, you train a generator on the real data and it produces artificial records, fake people with realistic ages, incomes, and behaviors, preserving the statistical patterns without copying any actual individual. Why do organizations reach for it? 3 honest reasons. Privacy. Sharing synthetic data with vendors or offshore teams feels safer than shipping real personal data. Scarcity. When real examples are rare, think fraud cases or rare diseases, you can generate more. And balance. Underrepresented groups can be synthetically boosted, a direct response to our representativeness lesson. Now, the 2 words that should govern every synthetic data conversation: fidelity and leakage. And here's the uncomfortable part: they pull against each other. Fidelity asks, how faithfully does the synthetic data preserve the real patterns? Too low, and models trained on it learn a cartoon of reality. But push fidelity too high, and the generator starts memorizing, producing records that are essentially real individuals with the serial numbers filed off. Sound familiar? It's our model memorization problem from Chapter 8, Reborn. Synthetic does not automatically mean anonymous, and regulators know it. Privacy claims about synthetic data need testing. Membership inference style attacks against the generator, nearest neighbor checks comparing synthetic records to real ones, not just a confident adjective in a slide deck. So the audit questions form a neat trio. Show me the fidelity evaluation. How was statistical similarity measured, and is it good enough for the intended use? Show me the privacy testing. What proves no real individual is recoverable? And show me the governance. Who approves synthetic data for this purpose? And is its synthetic nature documented downstream? Remember those dataset cards? Because here's the closing thought. Synthetic data doesn't remove risk, it relocates it from the data to the generator. And next lesson, we'll see what happens when nobody watches the relocation. Last lesson gave synthetic data its fair hearing. Today, the prosecution's case. Because synthetic data has 2 failure modes that concern auditors directly. It can amplify bias and it can quietly mislead the audit itself. Let's take them in turn. First, amplification. Here's the mechanism, and once you see it, you'll never unsee it. A generator learns the patterns in real data, including the biased ones, then produces unlimited fresh data expressing those same patterns. Train a model on that output, and the bias hasn't been diluted, it's been mass-produced. Worse, generators tend to smooth toward the majority. Rare groups and edge cases, already underrepresented, get rendered even more faintly, or as blurry averages that miss what makes them distinct. Now add the truly dangerous loop, using synthetic data to fix representation gaps. If the generator learned minority group patterns from thin real data, its synthetic minorities are low-fidelity guesses. The dataset looks balanced, the dashboards glow green, and the model has learned a fiction about exactly the people it already understood least. The gap didn't close, it got painted over. Second, misleading the audit. Imagine testing a model using synthetic test data produced from the same statistical family as its training data. Performance looks wonderful, of course it does. The exam was generated by the textbook. Or imagine bias testing on synthetic populations whose demographics were smoothed by the generator. The fairness metrics pass because the difficult reality was never in the room. And here's the subtle one I've actually encountered: documentation that doesn't clearly flag which datasets are synthetic. An auditor samples records, sees plausible customers, and verifies data quality on people who never existed. The evidence chain looks intact and proves nothing. So, your defensive habits. Always ask, is any of this data synthetic? And demand it be labeled in lineage and dataset cards. Never accept validation performed solely on synthetic data for consequential systems. Insist on real holdout evaluation. And for any bias correction use, ask what real evidence supports the synthetic minority patterns. Synthetic data is a power tool, and like every power tool, the question isn't whether it's dangerous, it's whether the operator respects it. We've met proxy variables twice in passing, in feature engineering and in bias hunting. Today, they get the full spotlight alongside their quieter cousin, staleness. These two feature-level risks cause more silent model failures than almost anything else. So let's master them. Proxies first, the full picture. A proxy is a variable that stands in for something else, often something you're forbidden or unable to use directly. Remove religion and caste from the model, and PIN code steps forward carrying much of the same signal. Remove gender and shopping categories, occupation history, or even name-derived features volunteer as substitutes. The model doesn't know it's being sneaky, it just optimizes, and correlated features are corridors it will always find. Here's the deeper point for your audits. Dropping the sensitive column is not bias mitigation, it's bias concealment. In fact, there's a respectable technical argument that you sometimes need the sensitive attribute available in testing precisely to measure whether proxies are doing its work. Remember our fairness KPI lesson and its privacy tension. So the audit question is, never did you exclude protected attributes. It's how did you test what replaced them? Correlation analysis between features and protected attributes. That's the evidence to request. Now, staleness, the time-based decay of feature meaning. A feature is stale when the relationship it captured no longer holds. Think about what the pandemic did to travel patterns, spending categories, and work locations. Overnight, features built on those behaviors pointed at a vanished world. Less dramatically, staleness creeps. A year since last address change feature meant stability in one era and means nothing in the gig economy. And operational staleness is sneakier still. The upstream system feeding a feature gets redesigned, the field's definition shifts, and the model keeps consuming numbers whose meaning changed without anyone telling it. Your fieldwork moves then. Request the feature documentation. Remember those cards? With each feature's source, definition, and last review date. Ask which features were tested as proxies and when feature relevance was last revalidated. Features are the model's vocabulary, and today's lesson in one line: audit whether the words still mean what the model thinks they mean. We've covered a lot of ground in this chapter, so let's do what good auditors do at the end of fieldwork: consolidate. Today I'll walk you through the practical checklist for evaluating data inputs, the questions in the order I actually asked them. Think of this as the chapter folded into a pocket. Start with origin. For each significant data source, 3 checks from our sources lesson: credibility with sampling evidence, legal rights with licenses that cover machine learning use, and lawful basis with documentation, not vibes. Then lineage. Can the team walk me from source to training set with transformations recorded? If lineage tooling exists, 10 minutes. If not, note the archaeology. Next, quality. Metrics on completeness, accuracy, and representativeness. And remember the sharper versions: who is missing, who verified labels, and does the training population resemble the deployment population, side by side. Then integrity, the tampering lesson, access lists on critical datasets, modification logs, dataset fingerprints, and my favorite single question: if someone altered 1,000 labels last Tuesday, how would you know? Then, bias. Was a bias assessment actually performed? Across which groups? Finding what? Leading to what actions? Check the hiding places, historical labels, measurement proxies, sampling skew, labeler consistency. Then features, the proxy correlation analysis and staleness review. When was each feature's meaning last revalidated? Then synthetic data. Is any present? Is it labeled in lineage? And was fidelity and privacy testing done? And never accept validation performed only on synthetic data. And finally, documentation. Dataset cards and model cards. Current, versioned, honest about limitations. Living documents rather than museum plaques. Here's how to use this in real life. You won't run every check on every dataset. That's not risk-based auditing. Pick the models that matter most, remember use case risk tiers, and go deep on their data. One rigorous vertical slice beats 50 shallow confirmations. That's been our method since the governance chapters, and it works because data problems cluster. Find one and its cousins are nearby. That closes the data chapter. Next, we audit the builders themselves, AI development and deployment. See you in chapter 11.